Hey friends, welcome back. Today in this video we will see one example on which lasso regression, or we can say L1 and N2 regularizations, right? What basically the ridge and lasso refer to? So ridge and lasso regression are no sum of the sample technique to reduce our model complexity, and we can say this is also useful to prevent overfitting, which may result from our simple linear regression, right? So basically what happens with ridge is that the cost function is altered by adding a penalty, we can say, that is equivalent to square of the magnitude of the coefficient. Okay, and whereas the lasso refers to the cost function for lasso, that least absolute shrinking and selection operator, that is a regression which can be written with certain no mathematical observation. So just like ridge regression cost function, so the lasso regression not only help in reducing overfitting, but it can help us to feature selection, right? So let's see one example by importing our matplot inline and numerical libraries numpy, also importing linear regression libraries that are linear regression along with our ridge and lasso, which are again in the same library function, that is in sklearn linear model, right? Here we will also use the R2 score, right, or the R square values to get that, and we can say we will also use to handle data in form of rows and column to get the pandas PD by using panda PD, and importing again plotting libraries and statical plot for seaborn as well. So we are using this car mpg data set again, which I'll be providing in the description also. And what I'm doing is, firstly I'm removing the car name that is not required in our ridge lasso regularizations, right? And next thing what I'm accessing is in origin, I'm telling that just replace 1 with America, 2 with Europe, and 3 with Asia. Secondly, telling that okay, get the dummies of this particular column as well, and replace all the question mark or these particular symbol with the np dot none values, right? And telling that just replace all other na with the median value. Now now we are separating independent and dependent variable, right? So how will you do that? First we will get the x, so copy all the predictor variables into x data frame, right? So in our case, as I have discussed in the last video, that mpg is a dependent variable, so we will drop it, right? Rest will be stored in the x, and copying the mpg column along with the y data frames, right? So the y will take this. Now we will import the pre-processing, right? And then we will scale all the column of the mpg data frame, so this will produce a numpy array. So here we will get that, and ideally the training and test should be here, right? So x scaled with have the all these x columns, right? Similarly for y scale, we will have the training and test, right, from the y column. Now again splitting my test set and train set, again here I'm dividing it with 70 ratio 30, right? So 30 will be for test size and rest will be for training. Now fitting a simple linear model. So again, how will you do that? In the last video as well, we have seen that how that thing is work. So calling the linear function in this regression model, right, and trying to fit the model with x train and y train, okay, and printing all the coefficient for those particular attribute. So it will give me that. Again we are intercepting or we can say getting the intercept for those for our model, right? So this is the intercept value. Now let's start with the a regularized ridge model, and let's note the coefficient how they give. So in the ridge we are getting the ridge and alpha value is 0.3, right? And saying that just fit that x train and y train with this ridge, so the ridge model will look like this, right? So here you can see that all the ridge coefficient are there. And similarly for lasso, what we will do is we will give the alpha values. This time we are giving 0.1 and fitting that with lasso and telling the lasso model with all these coefficient. So what is the observation here is many of coefficient have become zero, right, indicating the drop of those dimensions. Okay. Now let us compare their scores. So if we print the score from regression model score of X-train Y-train and for X-test Y-test, so here you can see that which is giving me 83%, and whereas for X-test Y-test it is giving me 85%, or we can say 0.83 and 0.85 respectively. Now if we print the ridge score for X-train Y-train and similarly for X-test Y-test, so again for X-train Y-train ridge score is also as same as we got with our regression model, right? And the X test Y test is also same as we got with our regression model. So there is nothing but a slight difference. So if we test the lasso score for X train Y test, right, and lasso score for X test Y test, so you can see that the lasso score is bit vary with the X train and Y train. Here we are getting nearly 0.82, and with the X test to Y test, so that is again more or less similar. So more or less similar result, but with the less complex model, right? So the complexity is a function of variable and coefficient. So now the lasso we get equally good result in test throw, not so training. Which further the number of dimension is much less in lasso model than the ridge or unregularized model, right? So let us generate polynomial models reflecting the non-linear interaction between some dimensions, right? So again calling the polynomial features from scalar pre-processing and telling that okay, here degree is 2, interaction only is also true. So that will give the polynomial features in that particular poly, right? And again we are fitting the transform with x scale from this polynomial feature, and again training splitting our train test set, right, with the 70:30. So here you can see that the shape that of X train. Now let's fit a simple non-regularized linear model on poly feature. So again to do that, regression model dot fit X train Y train that we just got from polynomial features, right, and printing the regression model of coefficients. So here you can see that these are the values. Same thing if we get with ridge. Same thing if we get with ridge. So here you can see that again 0.3 and the ridge model will give the coefficient like that. If we check the ridge score, so here you can see that this is the ridge score 0.91 for X train Y train, right, and 0.86 for X test Y test. If we get the lasso same, so for lasso you can see that it is 0.90 for X train Y train and 0.86 for X test Y test. Again the main difference is going with the X train Y train only. All right, so yeah, thank you.